Welcome to Real Analysis P6, Ordered Sets. An order tells us when one object lies before, below, inside, or divides another. Numerical size is only the most familiar example. Formally, an order starts as a binary relation on a set X. We write X precedes Y when the ordered pair X, Y belongs to that relation. The symbol may be less than or equal to, subset, divisibility, or something invented for the problem. Symbols do not enforce axioms by intimidation. A preorder is reflexive and transitive. A partial order is also antisymmetric. If X precedes Y and Y precedes X, then X equals Y. A total order is a partial order in which every two elements are comparable. Reflexivity compares every element with itself. Antisymmetry prevents distinct elements from preceding each other in both directions. Transitivity allows comparisons to pass through an intermediate element. Totality says every pair can be compared. Antisymmetric does not mean not symmetric. It says symmetry may occur only when the two elements are actually equal. The real numbers with their usual order form a total order. The power set of X, ordered by inclusion, is only partially ordered. Two sets need not contain one another. Positive integers ordered by divisibility also form a partial order. 2 divides 6 and 3 divides 6, but neither 2 nor 3 divides the other. Elements X and Y are comparable if X precedes Y or Y precedes X. A Haas diagram places larger elements higher and draws only the essential covering relations. In this diagram, the singleton sets are incomparable. The empty set lies below both, and the full set lies above both. Arrows and transitive edges are usually omitted. Apparently, even order theory has discovered visual decluttering. From a partial order, we obtain its strict version by requiring X to precede Y and X not to equal Y. A strict order is a reflexive and transitive. In a partial order, the strict and non-strict versions determine one another. For real numbers, these are less than and less than or equal to. The distinction becomes less typographically friendly when the order symbol is custom. A greatest element G lies above every element of the set. If it exists, it is unique. A maximal element M merely has no strictly larger element in the set. It need not be comparable with everything else. Every greatest element is maximal. A maximal element need not be greatest. Partial orders enjoy giving familiar words legally distinct meanings. Consider these four sets ordered by inclusion. The two upper sets are both maximal. Neither contains the other, so neither is greatest. Dually, we define least and minimal elements. Replace above by below, and preserve the same warning. Now let S be a subset of an ordered set X. An upper bound is an element of X lying above every element of S. A lower bound lies below every element of S. A bound need not belong to S. Forgetting this turns supremum into maximum and quietly deletes half of real analysis. For S equal to the open interval from 0 to 1, every number at least 1 is an upper bound. Every number at most 0 is a lower bound. The endpoints are bounds even though neither endpoint belongs to S. The supremum of S is its least upper bound. It is an upper bound, and it lies below every other upper bound. The infimum is the greatest lower bound. Both are unique when they exist. If the supremum belongs to S, it is the maximum. If the infimum belongs to S, it is the minimum. For the open interval from 0 to 1, the infimum is 0 and the supremum is 1. But there is no minimum and no maximum. Bounds and suprema depend on the ambient ordered set. The rational numbers whose squares are less than 2 have no supremum inside the rational numbers. Viewed as a subset of the real numbers, the same set has supremum square root of 2. Changing the universe can supply the missing boundary. A chain is a subset in which every pair of elements is comparable. The surrounding ordered set may still be only partially ordered. An antichain is a subset whose distinct elements are pairwise incomparable. In the power set of 1, 2, the empty set, the first singleton, and the full set form a chain. The two singleton sets form an antichain. An upper bound of a chain must lie in the ambient ordered set, but it need not lie in the chain itself. A well order is a total order in which every non-empty subset has a least element. The natural numbers with their usual order are well ordered. The integers are not. The entire set of integers has no least element. The real numbers are not either. The open interval from 0 to 1 has no least element. Well ordered does not mean neatly ordered, strongly ordered, or pleasingly arranged. It is one precise condition. A map between ordered sets is order preserving if x below y implies that f of x lies below f of y. It is order reversing if the comparison reverses. An order isomorphism is a bijection that preserves comparisons in both directions. Order isomorphic sets have the same order structure, even when their elements and notation look completely different. A partial order permits incomparable elements, a total order does not. Greatest and least elements belong to the set. Suprema, infima, and other bounds may live outside it. Maximal is weaker than greatest chains recover total comparability inside a partial order. Well orders guarantee least elements in every non-empty subset. Order theory begins when less than stops meaning smaller number and starts meaning whichever comparison the structure actually provides.